Chapter 34, number 51, asks, your camping buddy has an idea for a light to go inside your tent. He happens to have a powerful horseshoe magnet that he bought at a surplus store. The magnet creates a 0.2 Tesla field between two pole tips 10 centimeters apart. His idea is to build a hand-cranked generator with a rotating 5 centimeter radius semicircle between the pole tips. He thinks you can make enough current to fully light a 1 ohm light bulb rated at 4 watts. That's not super bright, but it should be plenty of light for activities in the tent. Part A asks to find an expression for the induced current as a function of time if you turn the crank at frequency f. Assume that the semicircle is at its highest point at t equals 0 seconds. Part B asks, with what frequency will you have to turn the crank for the maximum current to fully light the bulb? Is this feasible? Here's the figure that was given to us. As you can see, we have our 0.2 Tesla magnetic field, that's all these dots. Our 5 centimeter radius semicircle, which is up here. Our light bulb down here with 1 ohm resistance and 4 watts power. And our crank over here. Given the question, it's important to recognize that as you turn the crank and the semicircle begins to rotate around the axis of the crank, that the angle between the normal of the semicircle and the magnetic field, which is all these dots again, is going to change. And this will therefore produce a magnetic flux, which will then contribute an induced EMF and current through the light bulb. And from this we know that we should use Faraday's law to solve this problem. Now, since there was a lot of fluff in the question, I find it helpful to write down all the knowns. So we have here our magnetic field B equals 0.2 Teslas. The radius of our semicircle, now it was given to us in centimeters, 5 centimeters, and so it's helpful to change it into meters. So it's 0.05 meters. Our distance, D equals 0.1 meters. That was also given to us in centimeters. Initially it was 10 centimeters, but we changed it to meters. Our resistance, 1 ohm, and our power, 4 watts. We're going to start part A with the magnetic flux equation here, which is AB cosine theta, A being the area and B being the magnetic field. Now we can substitute 2 pi ft, which is just 2 pi frequency times time, for theta, so we'll have AB cosine 2 pi ft. Now we're going to plug in our magnetic flux into the EMF equation, which is just the absolute value of the derivative of the magnetic flux in terms of time. Once you take the derivative, you should have an equation that looks like this. And then you can plug in all of our knowns into that equation, drop the absolute values. It'll give you something like this. Don't forget, when you substitute for the area, it's a common mistake. We are doing the area of the semicircle, so don't forget to divide your pi r squared by 2. Now we're going to use the EMF that we just found and plug it into the current equation, which we have learned a while back. It's just current equals EMF over resistance. So we'll use this big long equation, plug it in down here, and divide by the resistance of 1 ohm. Once you simplify, you should get this equation. This is our induced frequency as a function of time if you turn the crank at frequency f. We're going to use the same equation for part B, only we're solving for the maximum current. So we know the maximum current is going to occur when sine 2 pi ft equals 1. So we can just drop that out entirely, which will give us just this equation. Solving this equation for f gives us this. Now we can use the power equation to solve for I. So we'll say P equals I squared times R. Solve for I, and then plug in the knowns for power and resistance, which is just 4 watts and 1 ohm. So that should give us 2 amps, and then we can just plug in that 2 amps into the equation up here, and that'll give us this equation, which will result in 405.28 hertz. So you will have to turn the crank with a frequency of 405.3 hertz in order to get the maximum current and fully light the bulb. It turns out this is not a feasible frequency to obtain by hand because hertz are a measurement of number of cycles per second, and obviously nobody could really crank out 405.3 cycles per second. So we know that 405.3 hertz is not feasible.